Moving on now to our next presenter is Liping Fu, is a civil and environmental engineering professor, a faculty member in the Transport Systems Research Group, and director of the Innovative Transportation Systems Solution, the ITSS lab here at the University of Waterloo. Professor Fu is also the principal investigator of many winter snow and ice control related projects funded by the Natural Sciences and Engineering Research Council, NSERC, the MTO, Landscape Ontario, and Salt Institute. I'd like to turn it over to Professor Liping Fu to share his wonderful talk. You'll have to unmute your microphone, please. There we go.
Okay, good afternoon, everyone. Thanks, Harold, for the introduction. So I'm just going to turn on my video camera. I guess it's already turned on, so you can see it's not a machine talking. It's me. And so I'm going to go to the slideshow. Can you see my slideshow?
Yeah, that looks great. Okay,
great. So first of all, I just want to say that I'm not really an AI guy. I'm not even a big data guy, but we do some work on the application of AI and big data. So that's what I'm going to talk about. As Harold introduced, and I'm actually a part of the transportation system group in civil and environmental engineering. We do a lot of work related to the infrastructure and the planning, design, and the management, and traffic operations, and the pavement, and so on. And so I have a lab and called ITSS lab. Sorry that the picture actually is not most updated. And so we have a bunch of graduate students and also postdoctors, research associates. And the picture, of course, here is snow covered, and as you can see that I do a lot of work on winter transportation that I'm going to actually touch on later on. And certainly my research is supported by many organizations, and I just want to acknowledge that. You know, transportation is really about movement of people and goods from A to B. Okay, but nowadays with all the connected device and we can actually see the movement and clearly, and there's a lot of visibility about this movement, and coming of course along with a lot of data. Okay, we call it big data. And so the question really is that how we can make the most out of this data and turn that into intelligence and help us to make a better decision in terms of planning and design and management. And the AI, of course, over the past decades, and certainly showing a lot of progress and also a lot of promise in terms of making this possible. Okay, and that was also the reason that why we also have been exploring this application of AI in the transportation engineering. So it's quite certainly it's not my area, but I'm very curious and I want to learn about the subject. And of course, the best way to learn is that doing it. So I created a few research topics and found money to basically recruit some student who has expertise in this area. And so first I want to acknowledge this former or current students. And they had worked on this project that I'm going to talk about. So I'm going to just give you a kind of flavor about what we have done in terms of AI application on three particular topics related to, first of all, the winter road condition monitoring and the road safety analysis, and the last one is traffic signal optimization. Okay, and so winter is really a big in Canada, and that's why I have been doing research on this for a long while. We look at all kinds of issues from top to bottom, okay, and look at the impact of winter on the mobility and the safety to the operation side, which is what's the best way to treat to do the snow ice control and different kind of salt, different kind of technology. Okay, and one of the problems that come along is really about monitoring. Okay, and what's the best way to monitor the load surface condition, okay? And it's of course, the reason is very obvious, okay? And for the government, they want to use this information, okay, to optimize the maintenance operations, and they want to measure the performance of the contractors. Nowadays, like MTO and a lot of provinces, they actually outsource the winter load maintenance to the private sectors. So they need to find a way to monitor that, the performance of that. And certainly that it's very important for drivers to know what's going on out there and before they make trips. And there's also a situation that if something happens and the government need to do this called due diligence check, see if they have done good work in terms of maintenance operations, okay. And the way currently being in the past that the conditions being monitored in the different ways, okay, and usually either by patrollers, okay, manually, or use this so-called RSC, okay, and load weather information system, which essentially is some sort of weather stations, and that particularly especially used for monitoring the highways, okay. So they have usually have sensors embedded in the pavement, and they have other sensors related to monitor the precipitation, temperature, and so on. And then this information could also come from the maintenance fleet or dedicated kind of friction measurement device. But in the early years, we found quickly that these are all quite limited, okay, in terms of spatial and the temporary coverage, okay. So we did some work on trying to come up with this so-called crowdsourced approach, okay, trying to make use of data from the road users. And the early days, we were thinking about ask the user to have some sort of cellular phone mount on the dashboard and take pictures, and then we do the classification, and then this information would be used subsequently for various purposes, okay. And so we did a lot of kind of testing, and especially the automatic classification algorithms, and the performance always kind of not desirable. I mean, the best days we could reach is around 80%, okay. So it's not very good, and then we of course we come across this the deep neural network, okay, that found success in many other applications, including image recognition, okay. So we saw that maybe we can test out this, okay, and so we tried out. The initial idea was really that there already many successful this deep neural network, okay, that have been trained, okay, for image recognition. And so the question, can we borrow them, okay, and for solving our problem? So we did that. We did a little bit kind of customization in terms of the output, and test out the different base models, and one from Microsoft, from Google, and another one is the BGG16. That's actually from University of Cambridge. And so we tested them out. And the fortunate part really is for us is that because we have been doing project with MTO for many years, and most of the projects involving some kind of analysis of alternative solutions. So we had to use some images, okay, from either from in-vehicle dash cameras or from this webcam, okay, from the RV stations. So we had kind of been doing that, and I usually ask some hire some undergraduate student to manually classify them, and so we have a database that kind of labeled kind of information, and that we can use to train these neural networks. Okay, so we did a few tests of different models as a base model, see which one give us the best result, and they're all quite good. Okay, in general, I mean, some is better than others, and so for example, for using this data from images from fixed cameras, like the traffic camera or web camera, and the performance that, for using the ResNet 50 as a base model, we can reach over 95%. So that's really, really good, and for what, the problem that we have been struggling with. And so we built a prototype systems that's actually live, and take pictures from MTO's traffic cameras and RSC cameras, and then do the online classification and show that information on the map and see what's the snow coverage. And so this is available. Actually, I'm not going to do demo because of time limitation. You can just go there. It's still live. Other than that, nowadays, of course, there's no snow. I would do this if if we had been a couple months ago. Okay, we still see a lot of snow on pavement. But now it's of course most of the bare pavement, so it's not really much to see. Okay, but this is could become a very powerful tool. Okay, because you can, it's a little bit like Google Traffic, except that we are showing the pavement, the snow coverage. Okay, and you can quickly see the spatial distribution. Okay, and where the snowstorms or what's left, okay, on the road with the snowstorm. And you can also look at the trend, okay, at each location, and you can find out that the snow coverage over time, and you can create alerts, when the bare pavement is lost or when the bare pavement is gained. And this, of course, very important for MT or other transportation agencies. Okay, they need to know that, and need this information for performance measurement. And so that's so this is a kind of very I would say small problem, but it's interesting problem that we see some sort of useful application. Okay, with deep neural network. So that's one problem, and the second problem I want to talk about is related to load safety. And interestingly, all the stuff that I'm talking about, it can all related to, okay, and we drive all the time, and we are the loader users all the time, and the safety is certainly a very big concern. Okay, and for all the loader users, and also for the transportation agencies who are responsible for that, for the transportation systems. So we do a lot of research on the loader safety side, which including identifies we so-called black spot or hot spot, and identify what will be the best safety measures to introduce and how to improve the load network in terms of design and the control measurement. Okay, so that safety can be maximized. Okay, all this kind of we call engineering work. Okay, that we do. Okay, we need some sort of models. Okay, to make a prediction about what will be the safety status of a given transportation facility. Okay, that could be an intersection or could be a load section. Okay, so that's a very critical aspect of the safety analysis. Okay, and unfortunately that this is a not easy problem. Okay, and I usually compare this is like to stock price prediction. And if you can predict stock price, you can get rich very quickly. And the same thing here. Okay, if you can do well, okay, in terms of collision prediction, okay, and you could save a lot of life, certainly that, because you can help to identify these locations and improve the safety, so you save lives basically. And so and this is a very hard research area, and a lot of models have been developed, mostly the traditional statistical models, and we also get about this. We did published a lot on this in terms of different models, how one is better than another one. And but the reality is that it's a very challenging problem, and the traditional models have a lot of limitations. Okay, and the model development process is very time consuming and rely on a lot of assumptions. And also more importantly that we do that once a while. Okay, like every couple of years, we do this sort of modeling exercise. So you're not necessarily taking advantage of this real-time data that comes in, okay, from the transportation systems. And so that was the motivation. We see that we want to explore, see if there are kind of new ways of doing that or make the predictions, and rely on this advancing the AI, okay, and see whether or not we can incorporate this real stream of data and improve the prediction, okay, and so on. So that's still an open topic, but we are still working on that. And one of the aspects we kind of worked on is to use the deep neural network, okay, to make a prediction about the collisions on a specific highway section or intersection, certain facility, okay. So one of the reasons of doing that is that, you know, as I mentioned before, we need some kind of prediction model, but traditionally, okay, we would have to develop specific models, okay, for different types of highways, for different jurisdictions. So for example, you know, here, you know, Waterloo, we would have developed our own models, and City of Toronto would have to develop their own models. And they have to develop models for, you know, intersections, roundabouts, you know, signal intersections, or, you know, arterials, freeways, and so on. Okay, so there's a lot of development work to be done. Okay, so we had this idea that can we actually, because this deep neural network, okay, it has a lot of parameters, a lot of learning capacity. Okay, and is it possible that we can just develop one, okay, to fit all the scenarios, okay, and all the needs? And so that was the hypothesis that we trying to test out. And so we did some work in terms of testing whether or not it's possible, and we put together collision data and from different locations, from different highways, and we develop a single model. Then we compare to this location specific models, okay, see how well this kind of, you know, single global model, okay, would perform. And we found that it's actually very promising, okay, and performance wise. And there's a few cases it's a little bit worse, but still difference is very small, okay. But in most cases they are actually significantly overperformed this the traditional, you know, location specific negative binomial model. Okay, so that was one of the aspects that we did. But the road safety itself in general, there are a lot of potential, okay, for AI applications, okay. And of course, you all know that, you know, from vehicle side, we are quite familiar with, okay, like Tesla or Google, okay, they're all doing the autonomous vehicles that essentially is application of you know, this AI for vehicle control. But from the infrastructure side, okay, we can also look at that there are many potential problems that we could address. For example, you know, we can use a camera to collect in the user activity data, which would lead to we can extract, okay, information about not just collisions, okay, but more importantly near misses and conflicts, which can tell us more, okay, about just from the collisions. Okay, so these are the kind of work that we are currently been doing, working on. Okay, I have some student work on that. So so the last one, okay, and sorry I run this very fast, but I just want to give you a sort of exposure, okay, on what we have been doing, and the intention is not necessarily getting to the details of this technical aspect, but just more on the application side. So I know that most of you come from different fields, so I think this probably would serve the purpose. So the last one I want to talk about is the traffic signal control. Okay, so this is the problem again. Most of us are very familiar with. We can offer some opinion about that, you know, the bad signals or the good signals. But this is a problem that we have to deal with, okay, as a traffic engineer, okay, how to time the signals so that we can achieve certain goals, okay, which could be improve the safety or improve the you know, reduce the travel time or delay at intersections. Okay, so there's a lot of work that have been done, but in general, the idea is that we want to decide the signal timing that either could be done kind of once a while or could be done in real time. Okay, and so that the vehicles that can follow this signal time plan will be safe and traverse through the intersections and would have the minimum delay, okay, or minimum number of stops, okay, and so on. So that problem itself is quite easy to describe, okay. It's just to decide the action of this signal heads, okay, which is related to certain timing plan, okay, and when to change the signal from green to red, okay. Of course, we also have to add the yellow in between. So that's it's an optimization problem, and if you look at the problem in a real-time sense, it could be a Markov decision problem, okay, which the system is represented by certain states, and it transits, okay, between states by over time based on the action that we take, okay, which is the controller, okay, the signal timing, okay, as the controller when to change the signal and so on, okay. And you know, most of the traffic signal nowadays, okay, if you are traveling in water or in any cities, okay, most of them are basically using this so-called fixed signal plan, okay, and which is, you know, basically that is a fixed plan for different time of day, because traffic volume change by time of day, so we have different time for that. But within each period, okay, the timing plan is fixed, okay, they do not react to the change in the traffic variation or what's going on in the network. So we thought that, you know, this is this, you know, change signal timing, that it's a little bit like a game, okay, in a way, and you can think about that. It's nothing, you know, fundamentally is like that, okay. You can adjust the phase transition so that you want to reach a certain objective, okay, or a certain goal, okay. So this could be easily mapped into a Markov decision process, and which can be solved, okay. It's just like a game problem, okay. So for this, I had a PhD student, okay, who worked on this problem over the past 4 years, and trying to develop some sort of this called applying deep reinforcement learning, okay, for traffic signal control, okay. And the algorithm that he tried out is basically started from the Google's AlphaGo algorithm, okay, and see if we can apply that for signal control purpose, okay. So that was, of course, you know, the problem. If we just look at a single intersection, and in order to implement this DRA, okay, you need to figure out the state representation and how to represent the state of the system, okay. And then you have to decide what sort of objective that you want to achieve, okay. So this is related to the rewards, okay. And then last one, of course, what sort of action that we can take, okay. So that's action space. And so the DRA model essentially is to map a certain state, okay. For a given state, what sort of decision is best, okay, at a given time, okay. And so that mapping, of course, is essentially is a problem to be solved through this deep neural network, okay, because there's a very large decision space, okay, in terms of the mapping from the state to the action, okay. And so that is really the challenge that the student trying to solve, okay. And so he tried out different ways of state representation, different kind of rewarding functions, and different training scheme. And so he also developed some sort of we call the simulation-based kind of training environment, okay, because we cannot experiment with a real signal control system. And just like AlphaGo, okay, you start with the training, okay, in a simulated environment, and then until you find satisfied, you could actually deploy that in the real world, okay. So here's a kind of give you a kind of demo of this simulation model, and show you that the system start to kind of just set up a random kind of signal timing, and then trying to observe what's going on. After that, then trying to do more random kind of setting and do the exploration, okay, we call it. And finally, it started training, and eventually it would converge, okay. So this is a short kind of animation show you that is this. If you notice that this actually is the intersection of University Avenue and Seagram, okay. And most of us are familiar with this intersection, okay. So this is a kind of a traffic model, okay, represented in a traffic simulation model called the VISM, okay. So you can see that in the exploration stage, it's just try out a very weird signal timing plan, see how the system would respond, and then collect information about this response, okay. So this is a exploration stage. Then you start to learn and adjust the parameters, and trying to see whether or not the performance getting better, okay. So in this case, the performance is actually on the right side, which show you the average delay, okay, per vehicle basis for the whole intersection, and see how the performance, this average delay, okay, it's a system-wide performance changes over the period of from the start from the exploration and the training, and finally when it converges, okay, to the training converge after the model is trained. Okay, and so you can see that eventually things are getting better. The long queues start to disappear. I don't see that very often anymore. And that essentially is an indication of that. But we have, of course, have quantitative measures of that in terms of queue length, in terms of average delay at the intersection, and so on. Okay, so this is I'm not going to wait for it to be run completely. And so we did a lot of tests, of course, see how the performance changes over different stage. And we compare to some existing models like fixed control. And another one is the actuated control. Okay, see if they're getting better and better. Okay, and so that's I just cover a very small part of the research. But the other problem, more interesting problem, which actually we also have worked on, is this called network-wide signal coordination. Okay, you have a bunch of intersections, and you want them to work together. Okay, so that when vehicles traverse through these intersections, they actually have averaging a minimum amount of delay, okay, a minimum number of stops. And so this is a more challenging, more interesting problem we have to deal with using multiple models and or multiple agents, okay, to do a coordinated control of that. Okay. So I think that my time is up. Sorry, I had to use the full time, and but really, it's a very interesting opportunity for this venue, okay, that had the opportunity to talk about something from transportation engineering, okay, not from cars or from other things. So so I believe that the next decade or so, there's going to be a lot of new applications come up, and it's going to change our field in general. So I left here my contact information if someone is interested, want to talk more, and I certainly I'll be more than happy to talk to you. Yeah.
Okay, thank you so much, Liping. We got about 4 minutes left, so I got a question for you here. I'm guessing with a collision predicting model, you probably have insurance companies throwing money at you. Are they sponsoring your research?
Not really. I would say that we are looking at more from the infrastructure point of view, not at the individual vehicles kind of level. And we look for them. The problem we are looking at is that we have a highway sections or we have a highway network. Okay, we want to know in general how many collisions per year that occurred on a given section or a given location. Okay, so we are not necessarily looking at the, as I said, at the individual vehicle level, which of course will be probably most interest to the insurance company.
Okay. Second question then, how does this all change with autonomous vehicles?
Oh, so that's autonomous vehicles is very much relevant to us, although we don't deal with the development of these vehicles in a specific way. We are more kind of looking at that if in our network, okay, with the increased number of autonomous vehicles, and or there's a mixed traffic of human-driven autonomous vehicles, so what will be the implication of that to the safety in general? And the other problem that we also are kind of interested, some people are working on, is looking at the connectivity side. We are all moving toward to this so-called connected vehicles, and vehicles will be able to pass information to other vehicles or to the infrastructure which we are dealing with, okay, and how we can use this capacity, okay, to improve the measurement and the control of that. And the other thing we are also looking at is that, although I haven't really done the research on that, is look at whether or not from infrastructure point of view, we can help to make this easier, okay, make this automation easier, and from the either the plan or the design and or operation of that. So there's certainly a lot of relevance to this new development, okay, and a lot of people are doing research on that.
Okay, well, that's great. Well, thank you very much for your wonderful presentation today.
Thank you so much. Sorry, I have to leave. Actually, I have another meeting, and so I will not be able to stay. And the next presentation, I happen to be interested, so I'll probably find another way to listen to that. Yeah.
Okay. Well, thanks again, and we'll transition on to our next presenter. Thank you very much.
Thank you.